This is Selfie. One file, 12,394 lines of C. It compiles itself, it executes itself, and it hosts itself. Inside that file there are four things. *C, a compiler that compiles its own source. Mipster, an emulator that executes its own machine code. Hipster, a hypervisor whose virtual machines can run the hypervisor. And the little library, all three of them run on. There are no dependencies, no framework, and no build system. Nothing is hidden below it. You can read all of it, and in one semester my students do. Here is the whole talk in 3 commands. Each one is a different kind of self-reference, and each one you can run tonight. The first, Selfie, compiles its own source to machine code, then it runs that machine code and has it compile the same source again. The two results are identical, byte for byte. The second, Selfie compiles its own emulator, and then the emulator executes itself. And the third, the hypervisor creates a virtual machine, and inside that virtual machine it runs the hypervisor. You understand the first and you understand compilers. The second, machines. The third, operating systems. That is the deal. So what is in the file? A path that runs all the way down with nothing in the middle left out. A scanner turns characters into symbols, a parser turns symbols into code. There is no syntax tree in between. Selfie generates machine code while it parses in one pass, which is much of why it fits. Then registers, the stack, procedure calls, a symbol table, and a linker that works in memory. And a disassembler to read back what it just wrote. Underneath, a runtime, a garbage collector, conservative enough to collect its own data structures, caches, a profiler, and a debugger that replays the instructions before a crash. The language has 7 keywords. The machine has 14 instructions. Now the idea underneath all 3 cells. It sounds like philosophy. It is the most practical thing here. What does a while loop mean? Not what the manual says. It means whatever the compiler emits, a comparison and a branch, and whatever the machine then does with those. Though the meaning of a program is fixed by another program, and that other program is written in the same language. Well, this is an English dictionary written in English. It is a paradox only if you insist the definitions come first. They do not. The machine comes first and the dictionary is bootstrapped onto it. Keep 2 colors for the rest of this. Ochre is syntax, notation, the thing you can check. Cyan is semantics, what actually happens, the thing you cannot. The first self, the compiler compiles its own source and gets the same answer twice. Start by borrowing a meaning. An ordinary C compiler builds selfie.c once. C* is a subset of C, so this works, and it is the only outside help the system ever gets. Or now use it on itself. That binary compiles selfie.c to machine code, call it selfie1.m. Its meaning still came from the foreign compiler. So close the loop, run selfie1.m and have it compile selfie.c again. Call that selfie2.m, a compiler compiled by itself. The two are identical, byte for byte. That equality is a fixed point, and it is where the system stops depending on anything outside itself. It is also the hardest test in the project. Change the code generator, and your compiler has to be good enough to generate the compiler that contains it. The second self, and a different loop for a different reason. Mr. is an interpreter for the machine written in C*. Fetch a word, decode it, do what it says, move the program counter. Combine mipster with *c and you get machine code for an interpreter of machine code. Load that into mipster, and mipster is executing mipster. And the inner one cannot tell. Code cannot ask whether the processor underneath it is silicon or software, unless it can see a clock, which is the one thing that gives an emulator away. What it costs is time. One instruction up there is a few thousand down here. Printing a usage line takes 86,000 instructions on the bare machine and 222 million when a mipster emulates the mipster that runs it. The third self, and this one is genuinely hard to build. Hipster does not interpret anything. It creates virtual machines and asks the machine below it to run them by context switching. Save these registers, load those, go. Its virtual machines are good enough to host all of Selfie, the compiler, the emulator, and Hipster itself. Stack as many as you like. in any order. That is what self-hosting means, and Selfie does it recursively, which most production hypervisors do not. One rule: every tower stands on a mipster. Context switching has to come from somewhere, and stock hardware does not offer it in the form hipster needs, so the bottom of the stack is always an emulated machine. Which brings us to the part I would keep if I only had 5 minutes. There are two ways to build the same operating system, and the difference between them is why operating systems have a reputation for being impossible to understand. By emulation, the operating system contains an interpreter. Guest instructions are read and carried out by the operating system's own code. The guest never touches the processor. Isolation is free because the guest is only ever data being read, and data cannot escape. By virtualization, the operating system sets up a page table and a timer, then lets the guest run on the real processor, taking control back on faults, calls and interrupts. Now isolation has to be constructed, because the guest and the kernel share the same hardware. And here is the claim. An operating system built by emulation is semantically equivalent to one built by virtualization. Not similar. Equivalent down to every bit the guest can observe. There is no experiment the guest can run that tells them apart except by looking at a clock. And this is not something I am asking you to believe. It is something you can measure on a laptop in about a minute. Most Selfie on an operating system built each way. Under emulation, the guest executes 86,380 instructions. Under virtualization, 86,380, the same number because it is the same computation. Selfie even ships a procedure called mixter, which switches a running machine between the two mechanisms mid-execution. Nothing notices, because from the guest point of view nothing happened. Which has a consequence worth stopping on. If the two are equivalent, and one is dramatically simpler, then the simple one defines what the complicated one must do. Build the emulated version first and you have a running answer key for the virtualized one. That is not a classroom trick. It is how parts of real operating systems get verified. An interpreter as the reference and the fast implementation checked against it. So if the two are equivalent, why does every operating system on Earth choose the hard one? For exactly one reason. Performance. Then guess same output, the same 86,000 instructions of actual work. What differs is the bill sent to the machine underneath. Or metal 86,000, virtualized about 200 times more, with another monitor underneath 700 times. Emulated 2,500 times because interpretation costs a few thousand instructions per instruction. So virtualization wins by a factor of 12 here, and by far more on real work, because the cost of a context switch is fixed and gets amortized. Give the guest something substantial to do, like compiling itself, and the overhead falls from 200 times to 1.7. Production systems get close to 1. That is why the cloud exists. And now the price. Virtualization is emulation plus self-reference, or the kernel runs on the same processor as its guests. To be isolated from them, it must itself run in a virtual machine. And who manages that one? That is the bootstrapping problem, and it is where the difficulty of operating systems actually lives. Real systems answer it with kernel code that never uses the abstractions it provides. It must not fault because it is the thing that handles faults. Or shrink that to the minimum, and what is left is a microkernel, the trusted base everything else stands on, small enough that people have proved it correct, or the whole part in one line. Emulation is isolation, virtualization is isolation plus self-reference. Take the self-reference out, teach everything else against the simple design, then put it back on purpose, and you can see the hard thing on its own instead of tangled up with paging and scheduling. That is what nobody told me when I was a student. Boys. There's a second half to Selfie, what a machine can decide about a program. Rice's theorem from 1953 says every non-trivial question about a program's behavior is undecidable. Questions about its text are safe, questions about its meaning are not. So every useful tool is a deliberate approximation, and Selfie ships several to compare. And that does symbolic execution, turning machine code into a formula satisfiable exactly when some input makes the program fail. Beta does the same as bounded model checking and adds memory access outside the blocks you allocated. Auto takes the full instruction set rather than the teaching subset and generates models that let you synthesize code rather than only check it. Bitme is a concurrent model checker over those models, driving solvers and binary decision diagrams. Beetle draws the formulae as graphs so you can look at what your program means, and there is a Rust implementation with a browser visualizer. Every one is self-applicable. Each translates code including all of Selfie and including itself. You can hand a symbolic execution engine its own machine code and ask a solver about it. And then you hit the wall, which is the fun part. Deciding whether those formulae are satisfiable is NP-complete. You can watch syntax become semantics and run into the limits of computation before the coffee gets cold. Which leaves the question everyone is holding. Why learn this when a machine will write the code for you? Or can't, because generation got cheap and verification did not. Producing plausible code is nearly free. Deciding whether it is right is as hard as it was in 1953, and Rice's theorem does not care who wrote the program. Value moves to the two ends, saying precisely what should be true and establishing that it is. Because the stack did not disappear. Every model that writes your code runs on virtualized machines compiled by a compiler, scheduled by a kernel. When it is slow or wrong or leaking, the person who can go down there is the person who fixes it. And because depth is not downloadable. Knowing where a field is thin and where it is about to give comes from having lived inside a subject. Selfie is small enough to live inside all of it. Only twos. The frontier is not proving things inside a language. Machines are formidable at that. It is finding the truth you cannot yet prove and building the language that captures it, which is the argument of a companion lecture if you want the long version. So 15 minutes from now you could be running a compiler that compiles itself. Clone it, type make, and run the third command. No C compiler, there is a Docker image, no terminal at all, it runs in a browser tab. Then open the source, find the last line before the exit code and print your own name. That is assignment 1. And it is genuinely how the course starts. There is a book that builds all of this from bits and bytes, classroom slides, and an autograder that grades your work before you submit it. All public, all in the repository. The full talk this is cut from is at selfie.cs.uni.salzburg.at/talk. The code is on GitHub. Come and take a selfie.